ready for this? All right. I'm going to ask you an English word. Forget math right now because we're going to define it mathematically. If I call you an independent person, what does that mean? Right, what'd you get? Not relying on something else. Anyone else have a different way of saying that better? If you're independent, you're not relying on someone else or something else, right? So if you're dependent, what would that mean? You rely on something else. We have that same type of concept when it comes to probability. Are you guys with me on this? Okay. So we're going to go and we're going to build stuff up a little bit. And then we are going to probably confuse you a little because we're going to learn when something is independent or dependent in probability. So in math statistic world. Okay, something's independent, relies on something else. Dependent, or independent doesn't rely on something else. Are you guys with me on that? And you're going to learn how to mathematically show this. What I don't like about this lesson, I'm showing you two different ways to do the same thing. Normally, a math teacher, we pick our favorite method and we're like, go. There's two different ways to do the same thing, and you have to be able to do both ways for the quiz. Are you guys with me on this? Okay, good. So, let's go, and let's see if we can work with the idea of independent and dependent. All right, so here's the first thing, and I think you're going to see where Ryan came up with just life actually goes correct with statistics. When two events are independent, the outcome of one event has no effect on the outcome of the other event. So if you're dependent, doesn't one affect the other? Doesn't one depend on the other, right? So there is an effect. Now, I'm going to give you some examples, and we're going to decide if something is independent or dependent just naturally. And then we're going to do mathematical ways so you can always prove it no matter what, if something's independent or dependent. Okay, so I need you to take you into your world here just a little bit, my friends. And let's just say that you have simple probability. We have a bag. You do not have to draw this. This is just me being very creative here. And we have marbles put in there. And you're just doing that lovely game of, putting it in the bag, reaching your hand in without looking, and pulling out a marble. All right? So we know that we have 6 green ones. 1, 2, 3, 4, 5, 6. And we're going to end up having 3 blue. 1, 2, 3. And then we had 5 reds. So 1, 2, 3, 4, 5. Now, in the real world, would I have those all mixed up with each other? All right, so just know those should be all mixed up. Now, here's logical. I want to see if you guys get this. What's the probability if I'm putting my hand in that bag and I pull out the probability of a red marble? What do we get? Give me the, guys, you know I prefer fractions. So what's my fraction here? What do we get? 5 over what? 14. Okay, now give me the decimal. Who was giving me the decimal? I think it was Eli. What was my decimal? Yeah, 3.3571, or about 35.71%. Okay, so that's the probability of a red one. Now, doing the same type of idea here, and I wrote too big. I should have put my diagram over here. I'm going to fix this because it's going to drive me crazy. Here's my example up here. Have you guys figured out how to use your selection stuff like that when you're doing your homework? How to make it so much nicer? Yeah, it definitely helps a lot. It says, what's the probability of selecting one green marble from this bag? What's the probability of getting a green one? 3/7. So it's good. 6 over 14, which gives me what? 3/7, which is now what? 0.42. So 0.428, and I'd probably go 6 here just for that. And what do we get for percent? 42.86%. Okay, now, why am I going 2 decimal spots? Here's just a hint when you're doing your math. if I do this and I say, please give me a percent to the nearest hundredth, don't you initially have to have 4 decimal spots? So just know, rounding wise, how many spots you should have if you were changing this. Now, here's my question for you. If you select one red marble from the bag first and replace it, what's the probability of selecting one green marble? So if I take a red out and then do what? Put it back in. Okay. What's the probability of a green? It's still 6 over 14 or what? 3/7 or whatever our decimal was. Did it really change? No, because what's the deal? I still have the same number of marbles to start with. So what I'm initially pulling from is going to be that case. Now, in this case, if I select one red marble and then select a green marble, but I replace the red one, these are called independent, because if I throw the red back, does that change anything? No. So that's going to be an independent event. So this is independent. Now, we're going to change it up slightly. Now what happens? Let's look at this scenario. Suppose you took that red marble from the bag first, but you don't replace it. I put it in my pocket. I don't replace it. What's the probability of getting a green one next? So think about this. So this is the probability of green if not replacing what? Not replacing red. So I want you to look at the quick visual of this. I took out a red. Oops, totally took too much out there. That's what I get for not doing finesse. Let me go this way. Finesse. I took out one. Right? I didn't replace it. What's my probability of selecting a green now? This time I get 6 out of what? 13. What happened? We lost one. We lost it. So the total what? The total changed. If the total changed like that, did me not replacing the red have an effect on the probability of getting the green? So this just became what type of an event? Are you seeing where this comes from? Okay. So we have a dependent event. Now, I don't want to have to think it through. I want mathematically to be able to do it so I don't have to spend tons of time. Okay? So we're going to build up the methods. There's 2 methods. There's multiplication method and there's a conditional probability method. Okay? Deep dark confessions, I like the probability, conditional probability method the best because that's what I taught when I taught AP statistics years ago. So I have a preference of the 2, but they're both good. Okay. So we're going to do an example of doing this using multiplication, okay? Now, guys, stay with me and just build up this as we go. Can you do that? Just know that some of this you're like, she's taking forever. It's a build up to get to example where we need to go. So we're going back to doing some stuff that we did before. We're keeping it really simple. Did I throw this somewhere? All right. Yeah, I got it here. All right. So we're going back to flipping a fair coin right here and rolling it up, right? So we have a coin and a dice. Are we good? They're both fair. There's nothing uneven. We're all balanced. I'm not trying to cheat you. Everyone good with that? Okay. So let's go with what we go first. If you flip a fair coin, what's the probability that it lands heads up? The probability of heads is 1 out of 2, right? Heads, which we know, and you guys literally told me this right away. You said it was what? 50 what? 50%. Great. So far, so good. Everyone agrees we're great. Good? All right, next one. What's the probability of rolling a 5 on a 6-sided number, so a normal dice? We know that's going to be 1/6, right? Which is about 16.67%-ish that we were looking at it. Right? So, first of all, here's my question. Should flipping the coin affect what I roll on the dice? Should it affect? If I flip a coin, should it affect what I roll? In our heads, we logically are going, this shouldn't matter. Right? So, in deep down, we know these are what type of events? Beautiful. Okay, I'm just making sure you're following with me and you're going where this is going. So, here's what we're going to do next. It says, if you flip a coin and roll a standard six-sided number cube, find the probability that the coin lands heads up and the number shows a 5 by answering the following questions. Okay, so now it's not just the coin or just the dice. It's what? Both. So we first have to get a sample space for this. All right, so let's think about sample space, and then we're going to keep it pretty easy. H means heads, T means what?
Tails.
1, 2, 3, 4, 5, and 6 represent the sides of the fair die. Are we pretty good with that?
Yeah.
So I want you to think about what could happen. I could have a heads, and I could also roll a what? Any of the numbers, right? So you agree with me, one time could be heads and 1. Then I could have heads and 2. Are you guys seeing where we're going with this?
Why?
Heads and 3. What?
Why is there an N again?
That's not an and, that's an and. Oh, okay, so that is going to be working with it, our intersection. So we have our heads and 4, heads and 5, heads and 6. Now, those are possibility if I flip what first? Heads. But what if I don't and I flip a tails? So do I have that same type of scenario, but I can do tails then a 1 and roll a 1, or tails and roll a 2, correct?
Yeah.
So we got heads and tails and 1, tails and 2, tails and 3, tails and 4, tails and 5, tails and 6. Okay. Now, how much do I have in my sample space? How many different options do I have? 12. Basically, 12 different outcomes I could have. Great. Now, think about when you're working with this. What's the probability, if this is my sample space, that I would get a heads? Well, how many things do I have to choose from? 12. But 6 of them would give heads. Oh, wait, what does that give us? 1 half. Now, what's the probability that I get roll a 5? Which is, give me a little bit better than that, but like, it's going to be 2 out of what? 12, which is 1/6, which is what percent? Like this I know is going to be 50%, but that's going to be 16.67%. It's a little bit bigger than 60%. No, stop. All right. So we got 16.67%. Great. Now, when you are working with this, determine the next thing with me. What's the probability that a flipped coin will show heads and a rolled number cube will show 5? What's the probability of heads and 5? 1/12. Would you guys agree with me on that? Which is about, this is a weird decimal, 0.0, is it 008? No, 0.8, sorry, 3. So it'd be about 8.33%. Okay, so we've got our values. Oh, look, how is Mrs. Ferguson showing work? She's showing it with fractions. Oh, that's what I want for you guys to do as well. Okay, so we have those. Now, here's how we can use stuff to our advantage, okay? So here's where we're going. How could we use the probability of heads and the probability of rolling, so flipping a coin to get heads, and probability of rolling a 5 from part 3, okay, to determine the probability of a coin showing heads and, a probability of flipping a coin getting heads and rolling a number cube to get 5. So how can I use these two to get this? How could I do that? Yeah, multiplying multiplying together. I like fractions better, Eli, but yeah, that's exactly what we do. Guys, look what happened. What's the probability of heads? That's what? 1/2. What's the probability of rolling a 5? 1/6, right? Isn't that what we got? 1/6?
Yep.
What did those multiply together to be? Which was what? Probability of heads and 5. Now here's my question. Does me flipping a coin affect me rolling a 5? No. So they're what to each other? If they're independent. So we know. The answer is no. They are independent. The events don't matter. The events, boy, let me at least write it so it's readable. The events don't affect each other. But notice, if they don't affect each other, is there a nice little formula that I can use? If they are independent, this is always true. The probability of one event times the probability of the other equals the probability of putting them both together. So, you have one event A, one event B. And if I multiply them together, if I found the probability of A and B, which is like the one that we did where we did the 1 out of 12, if those are equal, you know that they are going to be independent. Now, naturally in our hearts, do we know those were independent? Yeah. We naturally knew deep down they're going to be independent of each other. So this is what's called the multiplication method. You physically have to show that that's true. If it's not true, they're what? Yeah. So if they're not equal, then it's dependent. If they're equal, independent. Simple as that. It just takes time and work to show, okay? All right, let's do another one, and then we're going to practice a little bit. Now we're going to use my favorite method. We're going to use conditional probability. We're going to be using the same scenario because, remember, there's 2 different ways of doing the same thing. So I don't want to have to recreate the wheel too much, and I want to show you that it works the same way. Okay, so we're going back to the trial of flipping the lovely coin, which you guys have down really well at this point in probability world, and rolling a dice, okay? Let's answer the questions again. What's the sample space of doing these? Isn't the sample space of flipping a coin and rolling a die the same as what we've been doing? I actually don't like that color. So isn't it the exact same, my friends? So let's just rewrite it real quick just to make the point. We know their sample space is exactly the same. It didn't change from the last 30 seconds. And we have our tails and rolling 1, rolling 2. And we got our 6 now. And we know that our sample space has 12 total outcomes, just like we did before. Now, let's use conditional probability to figure this out. This is where it switches up just a little bit. Are you guys ready? Probability of heads from this sample space. So probability of a heads. What do we get? Probability of heads is still 6 out of what? If I just know I'm going to flip a coin for heads, isn't it still 6 out of 12? So we know that's 0.5 or what? 50%. Okay? Now, using this same information, I want you to think about this for a moment. What's the probability that a flip coin will show heads given that a rolled number shows 5? So the probability of getting a heads given what got rolled? A 5. Okay, so if that's the case, my sample space turned into what? My sample space before was 12. What's my sample space if I have to have a 5? 2 of them. I have heads in 5, and I have what? Tails in 5. And my 5s are looking really funky today. Didn't we just narrow it down? Because given, I have to have given, I rolled a 5. That gives me down to how many things? 2. So my bottom is 2, just like what we did when we did those circles and stuff, right? We simplify it down. So it's 2. How many of those are heads? That equals what? 0.5 or what? 1/2? 50%? Exactly. Oh wait, they're the what? Same. So here's the cool thing. Look what it's asking. Is the probability of flipping a coin and it's showing heads equals the probability of flipping a coin and it's showing heads given that the number cube shows 5. So I'm asking this. If I have the probability of heads, does it equal the probability of heads given 5? And what's the answer? Yes. If that happens, guess what your events are going to be? Independent. So, if the outcome of the number cube rule does not have an effect on the probability of flipping the coin and it's showing heads, the events are what? Independent. Now, so basically, here's the thing I need you to know. What stayed the same? The heads comes first. But it gets smaller when that is the case. Now look, it can go the other way around. This is what throws people off. I can still show that rolling a 5 and flipping a coin for heads are independent, but I don't have to do the example I just did. I could go a different direction. I can look the other way. I can sit there and change it to this instead. What if I have the probability, not highlighted, what's the probability of getting a 5 if I have my sample space, right? What was that going to be? 2 out of what? 2 out of 12, right? Because I have my whole sample space of 12, and then I'm just going to roll a 5. That's 2 out of 12. We know that's 1/6. Would you guys agree with me on that? Okay, now look at the next one. What's the probability that a rolled number cube will show a 5 given that a flipped coin shows heads? If I'm rolling a 5, given I have a heads. Guys, how many heads are in my sample space? Yeah, we're given, we have 6 because we have heads in 1, heads in what? 2, heads in 3, heads in 4, heads in 5, heads in what? 6. So my sample space didn't go from 12, it went from 12 down to what? 6. How many of those will give me a 5? Look at the question, next question here. Is the probability of the rolled number cube of 5 equal to the probability of getting a 5 given I flipped heads? Here's what I'm asking. Is this true? Is 1/6 equal to what? 1/6. So guess what? These events are definitely what? Independent. So that's another way of doing their independence. So since they are the same, if the probability of 5 given the probability of 5 given heads is exactly the same and unchanged, that means if having a heads affect my 5 rolls? The answer is what? No. Or the other way around. If I have probability of heads or I have probability of heads given 5, does rolling a 5 affect my probability of getting a heads? No. So those events are considered independent. So here's the last heads. They are, ooh, let me change colors. Gotta have some good color here. If the events are independent, if the probability of an event equals the probability of that event given another event. Or, notice this says what? Flip it around. It's still going to be the same. Here's what I need you to hear on this. You don't show both. You only need to show one of those two scenarios. Now, most people's heads are hurting, So we're going to have a little bit of fun and see if we can figure this out just a little bit. Let's do some examples. Are you guys ready to do some examples? Okay. All right. So let's have a little bit of fun, and let's just see if we can. I want to see if we're going to do a couple of these. I'm trying to figure out a good example without making this too hard. All right. How about if we do a deck of cards? Can we do a deck of cards? Okay. Here's the thing I need to know. Is the probability of pulling out a heads from a deck of cards. So here's a deck of cards. How many cards are in a deck of cards? 52. We don't include the jokers, all right? We're doing the same deck of cards, so it's 52. Okay. So what's the probability of heads and the probability of pulling out a 2? Okay. I want to know if those are independent of each other. Are you guys with me on that? What's the probability of pulling out a heads? Oh, not hearts, heads, not heads, hearts. What I wanted to say, hello, deck of cards. Hearts. Thank you. It's going to be what? 25%. How did you get that? What's my fraction?
1/4.
Yeah, 1/4. Because we had 13 out of 52, which is 1/4. Would you guys agree with me? That's 25%. Great. Now, what's the probability of pulling out a 2 from that deck of cards? 4/52, which is, I think, 1/13, correct? If I do my math correctly. So it's 1/13. I'm not going to worry about the decimal for right now of this. So, now here's the question. What's the probability of pulling out a heart that is a what? 2. What's the probability of pulling out a heart that is a 2? Yeah, because there's only 1, 2. That's a what? So 1/52. Okay. Now, if I use the multiplication method, this is the multiplication method process for this, okay? The multiplication method says if it's true, if I do this, these have to be equal. So guess what I just have to do? I have to test it. So I go probability of getting a heart. That's going to be 1/4. Would you guys agree with me on that? What's the probability of pulling out a 2? Okay, 1/13. Okay. Probability of heart and being a heart that is a 2, or 2 that's a heart, I guess, is 1/52. Do these two multiply together to be 1/52?
Yes.
So, are these independent or dependent? They're independent of each other. Kind of cool, right? Now, let's do the deck of cards example, but let's use conditional probability. So if I said multiplication, that's what I wanted to see. Are you guys with me on that? Now, what if I said, let's do this in conditional probability? All right? So, remember we have the probability of pulling out a heart, right? I'm going to put the word heart so I don't get the heads all confused. And the probability of getting a 2, all right, from a deck of cards. Now, to do conditional probability, you just have to decide which one you want to go with. Guys, do I want to go the probability of a heart and then figuring out the probability of the heart given pulling out 2 from the 2? Or do I want to go probability of a 2 equal the probability of a 2 given that there is hearts? Do you see how you can go 2 different scenarios? You just have to decide what conditional probability you want to do. So here's what I'm going to do. I'm going to let this be event A. So that's going to be my probability of a heart. And then I'm going to figure out probability, and this is going to be event B, A given B. Are you guys with me on that? Heart given what? 2. I'm just going to go that way. So let's do this real quick and see if we got this. Guys, probability of a heart. What do we get? 1/4. That didn't change from our last problem, right? 1/4. Now, what's the probability of a heart given that there is a 2? Okay. How many 2s are in a deck of cards? How many of those are a heart? Right? Are you guys with me on that? Did I do that right? Oops, 4. I forgot to write down 4. And then that 1, right? All right, does anyone now see where I'm going with this? Is the probability of the heart equal to the probability of a heart given what? Given a 2. Are they equal? So what are my events? They're independent. But what if I do that and I don't get them equal? They're not dependent. Are you seeing the difference between the two? That's why you have to learn all the stuff about conditional probability, all that stuff to do it. Now, here's where it gets nasty on your homeworks. Your Venn diagrams aren't just numbers put in. Your conditional tables, contingency tables are not just numbers put in. They physically put in the decimal probabilities for you. And then you have to figure it out. But that's using that idea. All right, can we do a quick stuff that you need to know for the quiz? Are we ready? Okay. The one thing I do want to say for your homework, when you're doing homework, it is normally not like 2 words. If you want to sit there and they're like saying, find the probability of, I don't know, let's go depressing again. Like that if you have used a patch or you don't use a patch, you can sit there and like label it A and B and then do your work so that way you don't have to rewrite everything over and over again. Is that fair? So like what I would have done up here had been like, oh, heart equals, oh, that's not what I wanted to do. Sorry. And you could do this on your homework. Why is this not liking me today? There we go. You could say heart is equal to A, 2 is going to equal what? B, and you can just use the letters after that point. I'm good with that. Long as you just label it so I know what things represent. Otherwise, when you're looking at homework tonight, you're going to be like, am I going to write a sentence every time I put my probability symbol up there? You know, that type of scenario. So you can do it. But make sure you work on that. All right, ready to talk quiz? What is the quiz over? All right, just so everyone hears me. It is 1/6 all the way through 110. On tonight's homework, I gave you, I'll double check after you leave, but I'm pretty sure I gave you the whole answer key again, so that way you can check yourself as you go. Are you guys with me on that? So that way you're prepared for the quiz. Because that's really hard to put something new on the quiz without you at least knowing if you understand it or not, right? So we're going to put this. So it's 1.6 or 1.10. Guys, guess what you have to know? Vocabulary, odds, chance, conditional probability, what's independent events, what's a dependent event, what's a two-way table, all that type of stuff, you got to know the vocabulary. What's the empirical rule? What's the normal curve? Are you guys with me on that? Those are all things that you have to know. So like for instance, what is the empirical rule? What shape do I have to have? Bell curve. My histogram has to almost make a nice what? Bell curve. Now, remember the empirical rule, is it 100% fact? No, it's a model. Everything is about or approximate. So when you're looking at your empirical rule, your lovely histogram has to make that lovely bell curve. It has to have symmetry. And when distributions or histograms or box plots have symmetry, what do we use to measure the center? We use the mean. Remember, that's your X bar, correct? So we have the mean. Should we be able to throw that in? Absolutely. Then we talk about standard deviation. And those are not equal, but I'm going to try to make it a little bit better. Okay. One standard deviation away. What standard deviation represents again? Yeah, the average distance from the average. It's how far you are from the average. Would you guys, I mean, that's the simplest we can get. The average distance from the average. How far away you are. All right? And when we do, with the empirical rule, we set it up so that we have our 2 standard deviations, I have our 3 standard deviations, and I totally did not draw this symmetrically. But you know what? I just have to go with the fact I'm bad at drawing. Okay. Sorry, guys, you have to suffer through this as well. Now, what does the empirical rule tell me? The empirical rule says, if I'm within 1 standard deviation on both sides of the mean, how much of my data am I using? I should expect 68% of my data is going to be there. Fair?
Yeah.
All right, perfect. When I'm with empirical rule wise, pick a different color. If I'm within 2 standard deviations of my mean, how much of the data should I be talking about?
95.
Now, is it always perfectly 95%? No, but it should be about that. So we were able to get that. So 95%. And then, what if I'm at 3? This is where you know my bell curve was not very bad. Okay. 3 standard deviations. How much of the data should you have?
97.
99.7.
Yay! Okay, great. Wonderful. Now, here's the other things you need to know. You should be able, with the standard deviations, be able to tell me what percent of data is used or not being used based off of that. For instance, what if I'm looking right here at this? How much data is being used? 50%. I know someone's like, that's simple. Because what does all of it have data up to? 100%. Okay, great. All right, what about now? What if I said, all right, I just want to find this much? 34%, because half of 68 is what? 34. What if, let's have a little more fun. What if I asked for here to here? It's not 84. What do we got? How much do I have from here to here?
34.
I've got 34% of the data on the left. Guys, how much do I have on the right? And this one throws people. I'm going from the mean to 3 standard deviations. What is it?
Whatever half is of 99.7.
So well, half of 99.7%, and that counts. Because where did I stop at? 3 standard deviations. I didn't go past it. Are you guys with me on that? So half of 99.7 is going to end up being, what is that? 49 point what? 85, right? That you're going to add to the 34. So be careful. They might ask you, what's the outside 5%? Well, outside 5%. Well, that's going to be here, and that's going to be what? Here. Like, again, please draw your bell curves better than mine. But that's the type of stuff you think about. Yes, Elizabeth. That's the empirical rule. It tells you where data should be about. The empirical rule is not 100% fact. Remember, like when we were doing that homework that day, you'd have like off by like 0.5% or not quite the right number of people. And then sometimes everything was within 3 standard deviations when it shouldn't be. It's just no. Empirical rule says this is what should happen if you have a normal distribution. And what's a normal distribution? A symmetric distribution where most of your data is around your mean. Make sense?
So how much percent is in like outside of the deviation? Is that like 0.3%?
Well, yeah. So this half would be over here, would be at 0.15%, and this one over here would be at 0.15%. Does that kind of help a little bit more with those guys? And then just doing all your probability stuff, chance, odds, make sure that things are going to be simplified. Quick thing just to review. Some of you are really bad at reducing fractions. Oh, did I say that loudly? Some of you are like awesome at reducing fractions. If you're not, can I show you how to save your height?
Yes.
Okay. You know the thing, this calculator that does all the work for you statistically? If you go alpha and you do the key next to it, it makes a fraction. And so you can put some big obnoxious number, let's say it was like 3,400. And you can sit there and say, I know that's the right probability. Mrs. Gregerson wants it as a fraction, not a decimal, not a percent. All you have to do is hit enter. Now this time I have no idea why it just did that. That is so weird. Actually, I put more than I wanted on here. Hold on. I wanted to actually go back here. It went that number. That's a really small number. I'm impressed. Okay. I wanted to be this number. Thank you. I want to hit enter. There we go. That's the one I wanted to do. But notice it does the work for you. So if you're really bad at reducing fractions, could you please let the calculator do the talking for you and work for you? You guys with me on this? because you have some larger numbers. Also, when you're working with decimals, make sure you're rounding them out that I tell you to round to. Okay? Yes, ma'am.
Wait, do you press second or no?
You go alpha instead. So alpha and then the one right next to it. So I want this green. I don't know if you guys can see this. You guys see that little green button right there on your calculators? That looks like a fraction over a fraction box over a fraction mark. If you go alpha, that's how you reach it. So you go alpha and then you hit the red one right next, the variable one right next to it. And you can do that for everything. Now here's some really cool stuff. And I don't know if I should show you all this now, but I love math, so we're gonna go there. Okay. So what if I asked you, and you put in the fraction in your calculator, but I asked you for a decimal? Do you realize you don't actually have to go 25 divided by 80? This actually can do the work for you. Are you guys ready for a magic button? It's called the math button. Look what it tells you it's going to do if you look at number 2. It changes it to a what for you? Decimal. What if I needed a decimal to be a fraction? Go back to that beautiful math button and look what it does. It reduces it down to you for 5/16. Does the work for you. I love calculators sometimes. They just do awesome stuff. Just know that you can do fractions. Just if you give me a fraction that's not in simplest form, it is wrong. Even when you're doing odds, okay? If you're doing odds, let's just say the probability of getting an A, I don't know. So the probability of getting an A is, let's just say, 5 out of 15. Okay. What's the odds of getting an A? What is you're gonna get? It's how many that are good to how many that what? Don't happen. That's now wrong. Why is that one wrong? Because it still needs to be reduced to what? 1 to 2. The odds of getting an A would still be 1 to 2. Does that make sense? So even when you're working with odds, just remember ratio notation is just another way of writing a fraction. It's just they still have to be simplified, but you need to make sure you have the number 12. Yes, sir.
Why is it turning into a decimal when I'm typing in
It's
fraction?
oh, I'm not sure why it did on that one. It shouldn't do that because we have it set to do fractions, but sometimes it just does. And if it does that, that's when I always go to the math key and let the math key do the work for me. I'm slightly lazy sometimes when the numbers are huge. But just remember, this would be considered correct when this one would be considered what? Incorrect. You did reduce. So reduce fractions or odds, but make sure you add it. Odds, I'm always going to ask you to do it with your colons. Okay? That's called ratio notation. Are we good? Is that going to give you directions for the quiz? All right. I would love for you guys, do you have any other questions about this? How about we work on your homework so that way tonight you can study for your quiz? Does that sound like a good plan for the rest of the period? Wonderful. I think that would be